Hello, everyone, and welcome. In this episode, we'll talk about physics with an episode about sound. What is sound? Do you know where it comes from, how it reaches us, and how it's influenced before we hear it? Can you redirect sound? Can you perhaps even send it to a certain location? We'll dive in the field of phononic properties and metamaterials today to get an idea of how sound can be controlled. You don't have any idea what we're talking about? Don't worry, that's totally understandable. As we delved into this area of science, we found ourselves in a maze of terms that we didn't know anything about. In this episode, we'll pinpoint and elaborate on a few things about this relatively new field of science. This was done with the help of Anastasia Krasinska, who gave an explanation for dummies. And next to me, I have Minke and Pavlo, and together we'll discuss the topics on an extraordinary field in the episode of physics called phononic metamaterials. Hi everyone. Hello, Minke.
Hello.
And Pavlo.
What's up?
How are you doing, guys?
All is good.
All is good.
Excited to make a podcast.
Yeah, definitely.
So I hear you guys were talking to Anastasia Krasinska about phononic metamaterials. Just as a first question, why would I care about this?
Okay, so basically, metamaterial that was so exotic at first that was deemed impossible. We're talking about metamaterials in general, but today we will zero in more into phononic metamaterials. And here, the applications are simply mind-boggling. Think about really controlling sound, not just damping it. So if you live near to an airport, highway, or train station, this might come in handy, but also about controlling heat. So think about perfectly redirecting heat and maybe even influence light. So basically we're talking about the master of energy and waveform. And if this is not really ringing a bell for you yet, that's totally fine, as we will elaborate in this episode. And also we have a little bit of a surprise.
We have phononic materials that can attenuate seismic waves.
So you're saying right now in a very covered way that you could somewhat influence earthquakes?
Not influence, but minimize negative consequences.
Oh, whoa. So that was Anastasia? Weird. But how do earthquakes fit into the research that we're talking about now?
Yes. There are a lot of branches in physics, and we have to look into this field a bit further. There are the Newtonian mechanics, which we all know about the apple and gravity, and we have nuclear physics. I hope you've all seen Oppenheimer, which is a really nice movie. And here we talk about an interdisciplinary field. So we talk about quantum mechanics, we talk about acoustics, and we talk about condensed matter physics, which is about solids and liquids. And when we look at the key characteristics of this new vague field, we have a very diverse methods and approaches. So we can look at empirical and non-empirical experiments. We can look at modeling and synthesis, which are the typical non-empirical approaches. So what Anastasia uses are methods from classical metamaterials and also chemical engineering, which is the interdisciplinary part. It's like a melting pot of methods and methodologies.
Anastasia Krasinska is a researcher who works at the University of Groningen. She works more specifically at the Faculty of Science, where she is conducting research in metamaterials with phononic properties to control sound, mostly. We asked her about her field of research, how she got there, and what she finds interesting about her field. So let's hear what she said to us.
Oh, it's a long story. Probably we do not have time for that. But I started from very theoretical research in the field of wave dynamics in my home university in Ukraine. And then I moved to the Netherlands to join my husband. There I got a postdoc position. And the postdoc position was linked to research on metamaterials. And since that time, so 10 years back from now, I'm in.
Nice. So a bit of professional and personal reasons combined.
Yeah. Very a strong mix.
Nice. I can see that. And but still, what would you say, or like, what do you find interesting about this field from a professional point of view?
There are a few very interesting to me points. So the first one is the ability to change the properties that were given by nature to materials and to manipulate them in any ways which previously were thought impossible. And second, the fact that we can prove that all these ideas work in real experiments. And the third is that we can apply these materials to solve some burning problems.
Okay, so in a sense, you can play God and also see your results, and it even has a benefit on a material level.
Yeah, can say it like that.
Okay, so we're talking about phononic materials. What is a phonon?
If you ask me, for my unqualified opinion, it's a synchronized vibration of particles in solids and sometimes in liquids. Or in easy terms, microwaves, as in tiny waves. So imagine a wave like on a water surface or something, but minuscule and also traveling through solid matter, not just the liquid water.
Phonons are energetic particles. Yeah, so it's not matter.
Yeah.
It's just energy which is transferred through fluids or solids.
Now that we know what phonons are, what is then the difference between a phononic metamaterial and a plain boring material?
Phononic metamaterial can control waves propagating in it, and plain boring material is passive in this sense. Yeah?
Okay.
So there is no control, wave energy just propagates as it should according to classical laws of physics, and in phononic materials we can break these laws.
So for those of you wondering, photons and phonons are closely related, and it's not just similarities of words. It might be a bit juxtaposed, but a photon is in this sense the electromagnetic wave or vibration, while a phonon is the mechanical counterpart, so an orchestrated mechanical vibration of many, many particles. Or is it?
The similarities are that their propagation follows the classic laws of wave physics, and the differences are in the different type of energies that they carry on. Yeah.
So phonons and photons both have a wave character,
Yes.
but the phonon carries a different energy. So a photon is electromagnetical. I hope all the hearers had a good background or somewhat background in physics, but we're just going to reiterate some things. And the phonon, on the other hand, has then what type of energy?
Acoustic energy, let's say, in very broad sense, because there are different definitions of acoustic energy, and depending on the field of physics.
I see. Generally speaking, the energy would be more of mechanical type.
Yes.
So it is super fascinating because phonons are also related to temperature or heat, as these are also mechanical waves or vibrations, but here apparently on a different scale. Heat or temperature is the even smaller wave counterpart of sounds.
Indeed. To control heat, we engineer phononic materials at the nanoscale. To control sound, we engineer these materials at centimeter, millimeter, and even meter scales. It depends on the frequency of sound. And if we talk about sound produced by very large objects like factories or airplanes, then we might need large structures to control it. And we do have them, even among normal materials.
Oh, wow. I see. Temperature and sound seem like two different things to me. How are phonons then actually controlling vibration and sound?
So it might appear somewhat complex, but bear with me. They do it through so-called band gaps. So simply put, if we imagine vibration in general as a person, the person gets lost in the labyrinth of the material. So more specifically, certain constellations of structures and material properties present somewhat of a wall for sound. This happens on two scales. So the material level, so the specific properties of the material, and on the structure level. So the microstructure of the material, which is created to influence wave energy specifically. One of these two labyrinths, so to speak, stops sound or vibration in its tracks. It gets rerouted and lost in the maze of the material. It's important to say here that usually not all sound is influenced, but only part of it, so certain frequencies. In measurements, this leads to bands in the recorded spectrum, so they are called band gaps.
Okay, so now I have a pretty good picture of the background, but what did Anastasia do? What methods did she use, and are these different from the rest of the field of physics?
This is what she said.
My methods are not very different, so it's combination of modeling, materials engineering, and experiments. What is different is the outcome that we get as compared to engineering traditional materials.
Yeah.
Because we have more active control over the properties of the final materials that we make, rather than just studying the properties of materials as they are.
Okay, so that sounds very diverse, and they get to play around more experimentally. Good for them. But what was the goal of the research of Anastasia?
In the paper called Dissipative Dynamics of Polymer Phononic Materials, which is about polymers, they were aiming at the following. So it's difficult, very difficult, when you look at polymers to predict their phononic behavior. This is because polymers have so-called viscoelastic properties. And the general approach of the article of Anastasia was to describe wave dynamics with the help of models. And the models that we nowadays have are oversimplified. So that was sort of the motivation to do this research, to find a complex model that will describe these wave dynamics in polymers. So to understand and predict sound and wave propagation.
The goal of this paper is to a little bit, how can I say it, to dissolve the magic around metamaterials. Because in metamaterials field, it's believed that we can use structure to control waves very efficiently and in predictive way, ignoring the material part. And in reality, these two components, they always come together. So the goal of this paper was to show that in polymers, we actually cannot forget about the contribution of material to the propagation of waves. And what we did there, we tried to marry two fields, so the physics of polymers and the physics of metamaterials, to show that they must be together to get accurate description of wave propagation in phononic metamaterials made of polymers.
Okay, so this research article of Anastasia describes an extensive way of the two fields of metamaterials and physics. To look further into the methods and methodologies used in this research article, we can say that this is sort of a mix between non-empirical and empirical research. So, in the first part of the methods of this research article, they try to grasp the theory of polymer characteristics. And next to this, they look how the structure of polymers are influenced by different temperatures and frequencies. This helps to see how the viscoelastic properties work. And then we have a non-empirical side. It's about estimating the accuracy of different models that can be used to describe the behavior of the visco. Researchers use fairly simple models, but also so-called multi-models, which are the more complex models that have several parameters for viscous characteristics. Next to this, we have the empirical approach, which is about experimenting. So in the last phase, experiments are done to validate the accuracy of the models. This is done with plates made of two types of polymers that are used as phononic materials. So it was the goal here to validate the importance of measuring geometric and physical parameters and to predict where certain band gaps are located. So the band gaps are the frequency ranges where the acoustic waves cannot propagate within the structure of, in this case, the polymers.
We used experimental techniques from two fields. So one from rheology of polymers. So we characterized the properties of polymers as good as we could. And we used ultrasonic testing techniques to characterize the dynamic properties of metamaterials. And of course, we used the modeling techniques to verify whether different models representing materials behavior can verify whether how accurate are different models in predicting the properties of dynamic polymers.
So there were some experiments done with the models about which I talked earlier, and two of the more complex models together can accurately predict where band gaps are located. Thus, researchers know where acoustic waves stop propagating, even in viscoelastic materials, which were the polymers. So these models can be used to predict where band gaps are located in different types of materials. And in the future, this can be used to even redirect sound. So the simpler mathematical models that were used, they were not sufficient in predicting this phononic behavior in the polymers, which were the phononic media.
All right, so now I understand something about the result of the paper, but how can these results help society further?
For the field, these results can help to understand the correlation between dynamic and mechanical properties of phononic materials and other characteristics, such as dielectric, thermical, and magnetic properties. So, how these properties relate to phononic properties. This is a bit of a mouthful, I understand, but this is also science. And in regards to society, there are very mind-boggling applications here. So for example, we talked about redirecting sound for airports, train stations, and so on. Or even, and this is very practical and very, very familiar, to redirect sound for flats and your neighbors. But there is one application which is even more crass, and that is the influence on earthquakes.
Another application is that we want to use metamaterials to control vibrations induced by trains. For that, you also need to know and to be able to model the dynamic properties of materials with very high precision. And as a side project is using metamaterials, and in particular 3D printing metamaterials, to develop new generation of sound barriers for highways, for airport applications, that also requires the knowledge of dynamic properties of the structure. And if we go even lower, below infrasound, we go to the frequencies of like seismic wave vibrations, ground-induced vibrations. Yeah? So seismic frequency ranges from 0 to approximately 10, 15, 20 hertz.
Yeah.
And yeah, we have phononic materials that can attenuate seismic waves.
So you're saying right now in a very covered way that you could somewhat influence earthquakes.
Not influence, but minimize
Yeah.
negative consequences. We cannot influence the source,
Yeah.
but we can use phononic materials to isolate buildings or foundations of the buildings from these waves by attenuating or redirecting these waves in the direction that can be more or less safe.
Wow.
For example, the direction there we do not have many constructions.
What do you feel like is up there in the future? What can we expect?
I have very high expectations about that, and currently I have 3 projects started that will rely on these results obtained in this paper. Yeah, because with this technique, we know the way how to use metamaterials, how to model them, how to predict their properties correctly, and now we can use this knowledge to apply these materials in different fields.
In very practical terms, this means that applications which were locked in before due to lack of modeling to basically manifest them to reality now will pour in. So people brace for many, many phononic metamaterial applications.
All right, I understand something now about phononic materials, and they might even help me protect my house against earthquakes. Great. Thank you very much, guys.
Yeah.
Yes, of course.
Let's do this. It was very nice.
Let's do this. Nice.
So to the listeners at home, thank you very much for listening to our podcast, and we're happy to teach you more about the coming episodes in our series.